Hello, so in this video we will talk about another application in which we can use vectors in two dimensions. So the problem at hand is something like this, that we have a regular polygon. And what is a regular polygon? A regular polygon is a polygon whose sides are equal to each other. Okay, and then if we have the regular polygon of n vertices, then we have the points p1, p2 up to pn denoting the coordinates of those vertices, and this is in vector space in two dimensions, and O is the center of the polygon. What we have to prove it, the vector sum of all the vectors from starting from center to the to each vertex is the zero vector. So what does the question mean? The question means something like this. We have, let's say we take a hexagon. Okay, so pardon my drawing here. Okay, and this is the center, and this is my p1, p2, p3, p4, p5, and this is my p6. So what I'm trying to say is that we have to add this vector, this vector, this vector, this vector, and this vector. If we add them, we should get a zero vector. This is what we have to prove. Now this is very intuitive, you can easily see that, but once we start proving it, we will see that it is a little bit involved. So let's start doing it. So let's say that our points are given by the ordered pair xi, yi. So this means that p1, the coordinates are, so without loss of generality, we can say p1, this is x1, y1. Okay, okay, and then we can say similarly up to pn, and the center point is the origin. So our center is 0, 0. Okay, now we talk about the angle. Now imagine that this is again, let me draw another polygon here, maybe a better one, not really better, but so let's say this is my p1 here. So what is the angle which is made by op1 to the x-axis? The angle is 0. What is the angle which is made from op2 to the x-axis? This is some theta. But what should be the angle for OP3? This should be just 2 theta, right? Because it's a regular polygon. So each increment in theta should be the same. So here we can say that we can assume without loss of generality that our first theta is 0, and since the polygon is regular, these four lines are the same things which I've just talked about, that the difference between the consecutive thetas is maintained. So in other words, if my first one is 0, the second one should be 2 pi over n. Why 2 pi over n? Because we have to cover the full 2 pi circle here. So we have the total angle of all these increments should equal to 2 pi. So then this is what we have. We have theta 1 is equal to 0, theta 2 is equal to 2 pi over n, theta 2 is equal to 2 pi times 2 over n, and theta n is equal to 2 pi times n minus 1 over n. So we say if OPI is equal to 1 for all I, okay. Okay, so then our job boils down to what? We have to prove that we have to prove what? We have to prove this, right? xi, x1 plus x2 plus xn, comma, y1 plus y2 plus yn. Okay, so this guy, this should be equal to 0. But xi is what? Xi is cos of theta I, and we end up with this form. This is what we have to prove. So now we have seen that this vector problem is now a problem of solving a little bit involved trigonometric identity. Okay, so then this is now our job to find. I'm going to find this one and leave the rest to the viewer here. Leave this one to the viewer. So what we are going to do is we are going to use a technique called telescoping. What is telescoping? That if we have a sum like this, we write it like xi minus xi minus 1, and this is I is equal to what, 1 to whatever. And so what happens is that this becomes x1 minus x0 plus x2 minus x1 plus x3 minus x2, and plus so on. So you can see here that this x1 will cancel out with this x1, this x2 will cancel out with this x2, and the last one xn will remain, and xn minus x0 is our answer. So this is our job, to write this summation in a form that we can use this telescoping story here. Okay, so what we are going to do is we are going to use the identity, this identity. So I'm going to, so we should multiply not by sine 2 pi over n, we should multiply sine pi over n here. Okay, so what we are going to do is our summation becomes 1 over sine pi over n, and we say I is equal to 0 to n minus 1 cos 2 pi I over n sine pi over n. Now if we use this formula here, this becomes, only I'm taking the summation right now, in the end we will divide it by this term. So then this guy is half sine of this plus this, so this becomes 2 pi over n I plus half, and I can say minus half sine of 2 pi over n I minus half, right? Okay, and then this term is there. Now you can see that what is the first term. So the first term is, I can take half out. The first term is sine of I is 0, right? So sine of 2 pi n times half minus sine of 2 pi n minus half. Okay, and then what is the second term? Plus, you will appreciate that the second term, one term will cancel out here. So second term is I is equal to 1. This is sine of 2 pi over n, 3 over 2 minus sine of 2 pi over n 1 over 2. Okay, so now you note that this term 2 pi over n 1 over 2 has a negative sign here and a positive sign here, so this will cancel out. So what is the last? So we can say this is equal to, it goes on and on and on. So our answer is half sine of, so what is the last term? The last term is when I is equal to n minus 1. So n minus 1, I is equal to n minus 1 plus half, so n minus half. So we can say 2 pi over n minus half, and then the first term, the negative sign here, we can say uh, minus sine of 2 pi over n minus half. Okay, so what is this guy? This is half sine of, this is 2 pi, just 2 pi. This is 2 pi n, 2 pi over n times minus half. 2 pi n times minus half is minus pi over n, correct? Okay, and then this is what? This is sine of, this is just minus pi over n. So what is any angle? 2 pi minus that angle is just that angle. So we can say half sine of minus pi over n minus half sine of minus pi over n, which is equal to 0. So the denominator, we don't even have to worry about it because 0 over anything is 0. So this way we can prove that this guy is equal to 0. So similarly, you can manipulate this guy by multiplying it by some trigonometric function. And changing the summation to this form. Okay, so actually you have just seen that this is a, I mean, the topic of discussion is vectors in two dimensions, but many times the problem, once you formulate the problem actually boils down to an algebraic or trigonometric problem. This is an example of that kind of a problem. Okay, so this is it about regular polygons and vectors, and how we can prove that the sum of the vectors starting from center to each of the vertices of a regular polygon end up being a zero vector. Okay, so hope it was easy to understand, and thanks for watching. Hope you liked the video.